public key cryptography. There is a fundamental difference between public key cryptography, between section 8.4 and section 8.1. In section 8.1, we discussed a couple of ways to encrypt a given text, but the problem with this approach is the following. If I give you a key to encrypt your plain text, you will be able to decrypt this text using same key. For example, over here, if you know K, you will be able to both encrypt and decrypt. Similarly here, if you know A and B, you will be able to encrypt and decrypt. This creates a problem. Imagine that I give A and B to the whole group of students. In this case, each student will be able to encrypt his or her own plain text. However, each student will be able to decrypt anybody else's cipher text. The greatest advantage of public key cryptography is the following. If I give this pair of numbers to all students, each student will be able to encrypt his or her own plain text. However, nobody will be able to decrypt anybody else's cipher text. So, you are able to encrypt, but you are not able to decrypt if you do not know the underlying plain text. So, we start with a pair of integers. This is a positive integer and this is a positive integer. Now, the number n is the product of two prime numbers. Moreover, this word is important. P and Q are not just some prime numbers. P and Q are large prime numbers. What do we mean by a large? A large means it is very hard to factor n without knowing P and Q. So P and Q are supposed to be gigantic prime numbers. The key point is, it is fundamentally harder to factor n than to find the product of P and Q. This idea is the most fundamental idea behind public key cryptography. Factorization is significantly harder process than multiplication. Next, the number E satisfies the following property. E and phi of n are relatively prime, where phi is Euler's function. Let me remind you what is Euler's function. It's over here. This is definition, and here is the formula. Note that we can easily find phi of n if factorization of n is known. Please take a look at the appendix. Once again, over here, we have the same formula. This formula. And now, in particular, if n is equal to pq, we replace n by pq here and here, done. And then this becomes this. So after we move p inside here and q inside here and simplify, we get this. So phi of n is equal to p minus 1, q minus 1. Repeat once again. If we know p and q, it is easy to find phi of n. Phi of n is p minus 1 times q minus 1. Since we know phi of n, it's not that hard to come up with a positive integer such that e and phi of n are relatively prime. Here is what we do next. To encrypt a message, we first translate the letters into their numerical equivalents. We use this table. Then form blocks of the largest possible size with an even number of digits, even because we replace each letter by the corresponding two-digit number. L is 11, K 10, J will be 0, 9, and so on. Now let us see how we encrypt. To encrypt a plain text block P, we form a cipher text block C by the following formula. C is congruent to P to eth power modulo n, where C is greater or equal to 0, lesser than n. So, in order to encrypt, we erase P to the power e, and then consider modulo n. This is C.
Yeah, I've got a question.
Yes.
How come you don't need to have n less than 26 anymore? Aren't you gonna have like some repeating residues? That was the reason in the last handout that you had n less than 26, right? It was because you didn't want to have the same residue for different letters. But now, since n is like way bigger, couldn't that happen?
Well, very good question. It's actually all the way around situation. Imagine that n is 100, and imagine that this is 50. Then C is 50, because C satisfies this. Imagine that P is 70, then C is 70. There is no escape. Let me give the opposite situation. Now imagine that this is small, say 10. If this is, say, 11, then C is 1, because C is lesser than n. You see it?
Yeah, I do.
So it's all the way around. If n is huge and this is not so big, there are no repetitions. Here is what we do next. The next natural question is, we use this formula in order to encrypt, but how do we decrypt? Well, here is the formula. In order to decrypt, we raise our encrypted text, our ciphertext, to the power d, and consider everything modulo n. Of course, question is, what is d? Here it is. D is an inverse of E modulo phi of n. Note that by Theorem 1 from section 4.2, D exists because E and phi of n are relatively prime. This is why we need this requirement. Now, let me go back to this section. Let me remind you what is inverse. Over here, this is definition of inverse. An inverse of A modulo M is a solution of this congruence. So, over here, since D is inverse of E modulo phi of n, D is a solution of the following equation. E times x is congruent to 1 modulo phi of n. This congruence has a solution because this and this, according to what is written here, are relatively prime. So, in order to decrypt, we have to know D. But nobody knows how to find D quickly if P and Q are not known. Repeat once again. In order to decrypt, we need D. However, if P and Q are not known, it is exceptionally difficult to find inverse of E modulo phi of n, because phi of n is P minus 1 times Q minus 1. This is the whole point about public key cryptography. We know how to encrypt. We have no idea how to decrypt without knowing P and Q. In order to encrypt, all we need is E and N. However, in order to decrypt, we need P and Q in addition to E.
Professor,
Yes.
the decrypting process, or sorry, even the encrypting process is still fairly like computationally strenuous, is it not?
Absolutely. We have to raise E, which is a huge number, to the power E. This is still quite a process, but this is significantly harder, fundamentally harder. Let us go back to this. If P and Q are huge, it's not so easy to find their product. However, it is fundamentally harder to factor n without knowing P or Q.
I have a question.
Yes.
So when we're choosing E, does the person that's encrypting the message choose E, or is that chosen by the person who owns, the private key D?
I give to everybody not one, but two numbers. I choose these numbers. I give you E, I give you N. What you have is your own P. Each student has his or her own P. Everybody knows this, but each person has his or her own P. Was that your question?
Yes, thanks.
Other questions?
Are the P's you're talking about still referring to like the 0 to 25?
So your question is, how do we create P? Is this your question?
Yes.
So let me go back to this section. Here is what we do. We start with some text message. Step 1, we replace each letter by the corresponding 2-digit number. For example, we replace T by 19, we replace H by 07, we replace I by 08, and so on. The resulting number is our P.
Oh, so P is that whole that string of text combined into one single number.
For example, if we have the following text, this, the number will be 19070818. This is the number we denoted by P, and we raise this number to this power. Let me make the following remark. Here's what we mean by form blocks of the largest possible size. If your text is huge, you can split this text into pieces first, and then convert each piece into a single number, which we call P. For example, if we have this text, either we convert the whole text into a single number, this will be P, or we convert this word into P1, this word into P2, P3, P4, P5, but of course, naturally, bigger the blocks, better is security. Therefore, over here, we say blocks of the largest possible size.
So we're combining words into one string, right? So then multiple words are either going to get broken up or they're going to get smushed into one long number. So how does the computer, or say like someone, decipher like where does a word end?
We can introduce a special symbol and therefore a separate number for space. Know that here we're not talking about symbols, correct? This is just an idea. So if you wish, we can come up with a separate number for space. Any other questions?
Is there any way to approximate Euler's function?
Of course we can approximate. It won't help. Here we need the exact value.
Okay. Interesting. All right, thank you.
Okay. But here is what we do next. Let us show that indeed d of c, which is congruent to this, it's over here, is congruent to the original plain text. That's the whole point. So question is, if we raise C ciphertext to the power D and consider modulo n, what is the resulting number? It turns out that the resulting number is congruent to P modulo n. But why is that? We have to prove it. So here is how we prove it. Let us start with D of C, decrypted ciphertext. According to what is written here, D of C is congruent to C to D modulo n. So the jump from here to here is thanks to this. Now, note that C is congruent to P of E modulo n. This is exactly how we jump from here to here. In short, if we raise both sides here to the power D, will get exactly what is written here. A left-hand side to the power d, it's over here, or right-hand side to the power d, it's over here. Next, here we put normal equal sign, because by algebra, p to the power e, the whole thing to the power d is equal to p to the following power, e times d. It's exactly what we have here. Next, we will discuss in a moment the following. ED, this, is equal to k times phi of n plus 1. We will discuss it in a moment once again. This is how we jump from here to here. Once again, we jump from here to here thanks to this formula. Lastly, by algebra, p to the sum of two powers is equal to p to this power, which is over here, times p to the first power, which is p. Conclusion. This is congruent to this, modulo n. Next step is to show that this is congruent to p modulo n. This will be shown in a moment. What we need right now is to explain why in the world this, which is over here, is equal to this, which is over here. Well, let us go back to the definition of D. It is said D is an inverse of E modulo phi of n. But once again, what does it mean, inverse? Inverse means a solution of the following equation, AX is congruent to 1 modulo M. In our case, A is equal to E. M is equal to phi of n. So with this in mind, this congruence becomes EX is congruent to 1 modulo phi of n. So D is X. D satisfies the following congruence. E times D is congruent to 1 modulo phi of n. Now, let us go back to section 4.1. Please take a look at this theorem. This congruence implies this. A is congruent to B modulo M means A is B plus Km. This is exactly how we jump from here to here. Since ED is congruent to 1 modulo phi of n, ED is equal to phi of n times some integer plus 1, which is over here. So, done. D of C is congruent to this modulo m. Once again, we are not done yet because we have to show that this is congruent to this. So, how do we show that this is congruent to this? Let us consider two cases. Case A. Plain text and n are relatively prime numbers. Well, guys, in overwhelming majority of cases, plain text will be a relatively prime with n because p is gigantic. N is even bigger. It's hard to imagine that two gigantic numbers have a common factor know that n is not even, n is odd, because n is the product of two huge and therefore odd prime numbers. So probability that the greatest common divisor of p and n is greater than 1 is almost 0. However, here, to be absolutely precise, we will consider two cases. Greatest common divisor is 1, and then in B, greatest common divisor is greater than 1. If greatest common divisor is 1, it is relatively easy to show that this is congruent to this. Note that by Euler's theorem, p to this power is congruent to 1 modulo n. Here is what we do next. Let us multiply both sides here by p. We get this. So this, which is over here, is congruent to this. Since this is congruent to this, and this is congruent to this is congruent to this modulo n, we are done. Now, as I said, this case is exceptionally rare. It is almost impossible to imagine that two gigantic numbers will have a greatest common divisor greater than 1. Oddly enough, despite the fact that this is a very rare case, it is significantly harder to show that this is congruent to p modulo n in this case. So here is what we do. Once again, step 1, copy this. The left-hand side is over here. The right-hand side is over here. We have this. Here is what we do next. So what is written here means the following. By definition of congruences, this minus this is divisible by n. But note that n is divisible by p because n is pq. So, since this minus this is divisible by n, and n is divisible by p, this minus this is divisible by p, which means this is congruent to this modulo p. Next. Now let us consider two cases again. So once again, in order to prove that this is congruent to this, we consider two cases, case 1 and case 2. Now let us split this case, case B, into two sub-cases. Sub-case number 1, P is not congruent to 0 modulo P, means P is not divisible by lowercase p. As we discussed in the appendix, we show that phi of n is equal to this. Here's the proof. We start with a general formula. Since n is equal to pq, we simplify this expression, we get this. So, phi of n is equal to this. Now let us go back to this expression. It's over here. We replace phi of n by this product, done. And then by algebra, p to this power is equal to P to the power P minus 1, the whole thing to the power Q minus 1 times K. Note that what is written here is indeed congruent to P modulo lowercase p. Here is why. Let us go back to Fermat's little theorem. It's over here. Fermat's little theorem says that if A is not divisible by P, note that this is exactly the case. This is not divisible by this according to what is written here. So, since this is not divisible by this, by Fermat's theorem, this, which is over here, is congruent to 1 modulo lowercase p. Now, in order to jump from here to here, we do two things. Step 1, raise the left-hand side and the right-hand side to the power q minus 1 times k. The left-hand side becomes this expression without p. The right-hand side is still 1. After that, if we multiply both sides by p, the left-hand side becomes the whole thing here, the right-hand side becomes this. So, in short, this implies this. Therefore, the left-hand side is indeed congruent to p modulo lowercase p. So, what we have right now is the following. D of C is congruent to P modulo lowercase p. So, once again, repeat once again. We have this. We want to show that this is congruent to P modulo n. What we have right now is the following. We just proved that this is congruent to P modulo lowercase p. Moreover, we proved it only in this case. Now, let us consider subcase number 2. Suppose P is divisible by lowercase p. Then, let's take a look at 4. Since P, which is over here, is congruent to 0 modulo lowercase p, if we multiply both sides here by this expression, the left-hand side here becomes this. The right-hand side here remains 0. So, if we multiply both sides here by this, we get the following. On the left, we will get this. On the right, we will get 0. So, this is congruent to 0 modulo p. Since this is congruent to 0 modulo p, and d of c is congruent to this, d of c is congruent to 0 modulo p. And now let us put pieces together. P is congruent to 0 modulo p. D of c is congruent to 0 modulo p. Since both numbers are congruent to the same number 0 modulo p, the left-hand side here is congruent to the left-hand side here. So D of C is congruent to P modulo lowercase p. Conclusion. It does not matter this is not divisible by p or this is divisible by p. D of c is congruent to p modulo p. But once again, this is not what we need. What we need is to prove that D of c is congruent to p modulo n, not p. How do we prove that? If we apply similar reasoning for the prime q, we will get this. Here's what I mean by that. Note that what is written here implies this, where instead of p, we have lowercase q. If here we have q, here we have q, here we have q, and so on. So, if we start from this, we prove two things. This modulo p and this modulo q. It's exactly what is written here. Here is what we do next. Note that this system indeed implies that D of c is congruent to p modulo n. Here is why. Any D of c of this form satisfies this system. Indeed, if you replace this by nm plus p, we'll get the following. Nm plus p is congruent to p modulo p, which is indeed true because this minus this is nm, which is indeed divisible by p. For the same reason, we can replace this by this, because nm plus p minus p is divisible by q. So once again, any D of c of this form satisfies this system. On the other hand, this system has a unique solution, modulo n, by the Chinese remainder theorem. Let us go back to the Chinese remainder theorem. It's over here. Please take a look at this. If we consider this system of congruences, where these numbers are relatively prime, indeed, p and q are relatively prime, then the system has a unique solution. So, this is a solution. This system has a unique solution. Therefore, D of c is indeed of this form, means D of c is congruent to p modulo n. Let me actually make two remarks. Remark number one. One can check that our reasoning in case B also applies in case A. But the reason why we still split into two cases is the following. Case B is very rare, and case A is much easier to prove. Lastly, because D of c is between 0 and n, 1, which is over here, implies D of c is equal to p. Remember, we don't really need congruence. The ultimate goal is to show that the decrypted text that we obtain using this formula is equal to plain text. We just proved this. It's congruence. There is no equal sign here. However, since D of c is between 0 and n, this and this implies this, and we are completely done.